is your box plot, box and whisker plot, or 5-number summary. You know, whatever you want to call it, looks like this: min, Q1, Q2, Q3, and max. And what we're going to do is we're going to look at the example from the homework, try and figure out which one of these is the right one. Now, of course, we know that the correct answer is B already because it happens to be starred. That's all right. We'll ignore that. Let's figure out ones that we can eliminate based on this 5-number summary. Which ones can I eliminate from this choice and why?
D.
D, good. Why D?
Because the maximum and the minimum are way too far.
Good. So the maximum goes up to 10, the minimum goes to 0, and that's outside of our data here. So cool, so we can eliminate D. Good. What else can we eliminate and why?
A and C for the same reason except for the minimum, but like both ones are too far.
A and C go up to a maximum of 9, but there's no 9 in our data set. So again, you can eliminate those. And once you've eliminated those, you can stop. The only choice that's going to work is going to be B. You can go back and verify that B is actually the right one. So yeah, a 1 looks good there, 8 looks good there. And then that's a 4. You know, that's not quite a 5, but then again, you're supposed to have a 5.5 and a 3.5. So those look reasonable for B. Well done. Thank you. Are we okay with that example?
Yes.
Thank you. Let's stay with box plots for a little bit. And let me ask you a question that kind of gets to the heart of what we discussed last week, and that's regarding this one. So I've got 3 different sets of data here, and in looking at these, one of the questions I could ask is, which one of these data sets most likely has the largest standard deviation? So let's remind ourselves something. What does a standard deviation represent?
How close the points are to one another.
All right, how close they are? Okay. And what makes a standard deviation bigger or smaller? Let me give you a hint. This is a problem that'll be on the exam next week and on the final exam. So make sure you understand what the standard deviation represents. So I think somebody started telling us, what does the standard deviation tell us in general?
Tells you how far one point, how the points are in relation to one another, like how spread out they are.
All right, good. How spread out the points are. In this case, the case of the standard deviation, it's how spread out they are from the mean. Now, is this middle bar, is that the mean? Not necessarily. It's the median, all right? But this still does give us an idea of how spread out the data is. And in fact, in this particular example, they're showing us some more things that a 5-number summary can tell us. So in this particular case, because the whiskers are the same length and the distance from the middle to either side of this box is the same, this distribution is symmetric. So the left and right-hand sides are mirror images of each other. How about this next one? This one is supposedly right skewed. And the reason it's right skewed is because there's a much bigger spread of data to the right of the middle half, or to the right of the halfway point, median, than there is to the left. So to the left, yeah, things are kind of squished together compared to how spread out they are on the right. So this is right skewed. And then conversely down here, we have left skewed. So to the right of the median, or Q2, this range is pretty small, or this range is much bigger in comparison. Same thing with the tail, or the whisker here, going from Q1 to the minimum. It's longer than the same whisker over here, going from Q3 to the maximum. So this one's left skewed. Now, going back to this, which one of these has the largest standard deviation? Anyone?
Wouldn't it be the one at the bottom, so the left skewed?
All right, I've got to vote for the ESC data here at the bottom, the left skewed one. That's right. Somebody tell me why. Why has this one got the largest standard deviation?
Because they're the most spread out.
Yeah, they're the most spread out. Now that spread is from the mean. And even though we don't know what the mean is, we can look at the min and the max, and we can look at how far things are spread out here, and we see a lot of variability. Now this box here, the range between the top of the box and the lower top of the, or the bottom of the box, is called the interquartile range, a big $10 word that I'm not going to hold you responsible for. But this box and the one up above are about the same size. But the big difference is that with the bottom one, there's much more spread in the data in terms of its range. If you take a look at the top minus the bottom, that's going to be a bigger difference than you're getting in the middle data set. So I would say that the left skewed data here, the ESC, has more variability than the NPC. Now on an exam, I'd probably make that difference a little bit more obvious. Maybe I'd have you compare, say, this one with this one, A and C, just to make the difference really obvious, as long as you know what you're doing. So are we okay with that one in terms of which one of these has the largest standard deviation? And just to reiterate, standard deviation reflects, on average, how spread out the data is from the mean. So, standard deviation reflects, on average, how spread out the data is from the mean. Now let me make that a little bit bigger here so it shows up on your screen a little bit better. Font of maybe 20. Should do it. And we'll go 22. There you go. Definitely make sure you know that for not only this exam, but for the final exam. So these 5-number summaries are pretty nice. It's a quick way to get insight into your data, into how much of a spread there is, what type of skewness there may or may not be, or if it's symmetric, that kind of thing. But there's other ways you can look at the data and find out, well, where's something at relative to the rest of the data set? We're going to go over 2 more ways you can compare something and get what's called a measure of position. How do you rate compared to the rest of your data? So the next thing we're going to discuss is percentiles. So let me switch over to the screen here. Before I do, are we okay with this one? All right. So let's look at percentiles next. Now with quartiles, the data was broken up into 4 chunks by 3 points. How many chunks do you think there are going to be when we start looking at percentiles?
100.
100. And how many points am I going to need to break my data up into those 100 little chunks? $99. 1 less than the number of chunks. So for percentiles, we'll denote this with like P.01, P.02, P.03, all the way down to say P.98 and P.99. So I'm putting in a decimal here, mostly because of stuff that we're going to do later on, and also because of the format of how to find this in Google Sheets. So there's going to be 99 percentiles that break your data up into 100 different chunks. So let's first of all play with it on Google Sheets. And maybe I should give you a little bit more of a definition. So for instance, P sub 0.13 is the 13th percentile. And it separates the bottom 13% of the data from the top 87%. So
is this kind of like the running example that you used last class, saying that like your friend is not your fault that he doesn't know? Okay.
This is exactly what we're doing.
Okay.
So yeah, I am doing a little bit of review in that class, in that sense. But P13 would look like this. You have 13% of your data here, your min, your max, P13, and then 87% of your data here. Now, what I want you to know is the difference between these two things. So let's take a look at another one. Let's say min, max, P.80. That's going to separate the lower 80% from the upper 20%. So on a test, a good problem to give you would be, okay, you get your results back from the SAT or the GMAT or the MCATs or whatever standardized test you're looking at. Would you rather your score be in the 13th percentile or the 80th percentile? Which one would you want?
Higher value.
Yeah, the higher value. And which one is that?
80th.
80th percentile. Good, good. Now the example you were referring to just a minute ago is when I did a race a number of years ago, a really, really hard race, and I finished in the 10th percentile. But when my friends were asking me about it, I was rather boastful of the fact, like, hey, I finished in the 10th percentile. Yeah, how about that? And of course, they in their minds were thinking 90th percentile. That's not my fault that they don't understand statistics, all right? I just didn't count on them being really sensitive guys to appreciate the effort there. Okay, let's review how to find those numbers. So with our current data set, let's find the 13th percentile and the 80th percentile. So let's see those here. Let's go over to Google Sheets to do that. Now the command you want to type in is equals percent, and it'll finish it off for you, percentile. So we want that one. I usually like to hit enter. That way it prevents me from making a typo. You have to tell it your data range. I already know that's A1 to A50. And then you need to tell it the percent as a decimal. And if you look at your Google Sheets handout, I redid this yesterday to include the fact that this has to be a percent as a decimal. So if I typed in 13 right now, Google Sheets is going to give me an error. It's not going to like it. It's going to say, well, no, error. So I go back, and there's really a couple errors. One's a typo, but it's expecting a decimal value here. So 13th percentile would be 0.13. If you type in a 0.13, now it should work. Let's take a look. So I'm getting 0.6. Is that what you're getting?
Yes.
Yep.
Thank you.
Can you do it one more time, please?
Sure. So start typing in the word percent, and Google Sheets should finish it up for you. Percentile. Actually, maybe it's not for me this time. And then you got to tell it where the data is. That's in column A, from A1 to A51, or excuse me, A50, comma. And then decimal point, 13. Does that help?
Yeah, thank you.
Yeah, no problem. So you should get 0.6. By the way, let's take a look at our percentiles here, and maybe you can give me a couple different names for P50. What would be another name for P50? There's two more names. What is it?
Midpoint.
Okay, but in our stat class, the midpoint had what name?
Median.
There you go, median. There's one more that I can think of as well. In fact, it's right on your screen right now. What's the other name for median or 50th percentile?
Q2.
Q2. Well done. So there's really three different ways you could calculate the median off of Google Sheets here. You could type in the command for median, Q2, or P50. Let's just double check that the command for percentile matches what I got here for Q2. So percentile, actually, it's got the same thing here. I'm just going to go edit this command and make that a 0.50. And bam, I get the same thing. So, yay. Nice. How's that one looking? Doing okay on that one? All right. So a lot of times we want to run this process the other way. I remember looking in a book on birth order and opening it up and skipping to the chapter that says only child. And the first sentence said, if you're an only child, you probably skipped right here to the book. And I felt really mad and embarrassed, but they got me. But a lot of times you want to know, well, what about me? How do I rank? So we can do this calculation in a different way. We can start out with a number and find its percentile. So let's start out with 10.8. What's the percentile of that going to be? Now, I don't know. Do you think it's going to be closer to Q20, I mean, P20 or P80? Where do you think it's going to be closer to?
P80.
P80.
Yeah, it should be closer to P80, okay? Especially since you're at the 41st spot in the data set. Now the command for this comes from percentile or percent rank. So as usual, you got to tell it the data range, but this time you're going to give it the value. You're going to tell it, well, what value are you looking at? So I'll type in equals percent rank. And once I get to the R, it can finish it off for me, percent rank. Your data is in A1 to A50. We want to know what's going on with 10.8. So that's the command that you're going to type in. And when you're ready, press enter. I'll leave it there for another second or two, but I think it's going to give us like 80.6 or something like that. Is that right? Let's find out. Oh, 81.6. So 0.816 or 81.6 percentile. Now, I'm not going to quibble with it why it's giving me this crazy value. To me, it kind of looks like the 82nd percentile, but you know what? It doesn't change the interpretation much either way. This is separating the bottom about 81 or 82% of the data from the top 18 or 19% of the data. That's the interpretation with it. So if you got your score back from the GREs, you know, maybe you'd be happy to be closer to the top than you are to the bottom. So, but that's the interpretation of this. It's the 81.6th percentile is what that value would be. Are you able to get that? Hopefully you're able to get that and interpret it. There is a homework problem just like this, asking you for the percentile rank of your data. And you would do just this. You can probably do it in StatDisk. I just don't know how or where. Just not something I've been able to figure out. And I'm not terribly curious, terribly motivated to figure it out. Let's take a different approach in looking at individual scores and try and understand how they compare to the rest of the data. And for this, we're going to look at something called the z-score. Now, in a sense, we've already dealt with z-scores, just not by that name. Let me tell you how they're calculated first, and then remind you of something that's relative to our test. You're going to take your data value and subtract off the mean. So first of all, you're comparing it to the mean, and then you're going to divide it by the standard deviation. And basically what it's going to do is count how many standard deviations away from the mean that you are. Now let me write down two things here. Population and sample. The actual formula that we're going to write down is going to vary depending on if you have population data or sample data. So if you have a population, then the mean is denoted with this Greek letter mu. That's your population mean. Divided by sigma, lowercase sigma, that's your population standard deviation. Population mean, population standard deviation. We have different symbols for these things if you're talking about a sample. What's the difference between a sample and your population?
Population based on a census, right? Or like a
population's based on a census, based on everything that has all the data that's in the set under study. Perfect. Thanks, Jalal. A sample is just some small subgroup of that. Could be small, could be large, but it's just not everybody. Jalal mentioned the right word. It's a census. You're hitting everybody. And just as a reminder, every 10 years, this country does a census. What is it? Technically, is it a census? Do we get everybody? Or does the census miss some people?
No.
Nope. You missed people.
There's a lot of people that get missed. And the Census Bureau does a lot of work to try and track down those people who don't fill it out and get missed. But inevitably, you're going to miss some people. Now, when you miss some people and you're only taking a sample, then we use different letters. X bar, that's your sample mean. S, That's your sample standard deviation. So, okay. Let's do some examples to try and get familiar with z-scores, understand what those are. And we're going to start with IQs. IQs, or intelligence quotients, have a mean of 100 and standard deviation of 15. So, okay. We'll do several examples with this. So the first one, sample, we'll call it example A. What is the z-score for someone if her IQ is 130? Okay. Well, that shouldn't be too bad. So you're going to take the score, the value, 130, minus the mean, so that's your 100 right here. So minus 100 divided by the standard deviation. And so by subtracting 100, we see that you're really 30 points higher. She's 30 points higher than the mean. That's what the numerator is telling us. Now, if the standard deviation is 15, 15 goes into 30 twice. Basically, what that's saying is that she's 2 standard deviations above the mean. 2 standard deviations above mean. So it's telling you how this person is positioned relative to the rest of your data. So 2 standard deviations above the mean. Nice. Let's do another example. Example B. Another person who didn't take Jeff Parent for stats has an IQ equal to 85. Find the z-score. Find their z-score. All right, not much different than what we just did, except this time it's z equals 85 minus 100 divided by 15. What's the numerator here?
Negative 15.
Negative 15. And overall, I get -1. Now, if you compare these two, if you compare the 2 I got here with the -1 I got down here, one of the things I wanted you to see is that one of them is positive and one of them is negative. What is the negative part of this telling you about this other score?
It's below the mean.
It's below the mean. Perfect. Now, one thing that means for you is that you've got to be careful that you subtract this in the right order. It's the data value minus the mean. Always. Always, always, always. But yeah, you hit it right on the head. This is below the mean. That's the important takeaway from this. Below the mean. Cool. Now, has anyone ever heard of somebody called Marilyn Vos Savant. Well, you're consistent with my other classes because they hadn't heard of them either. I guess probably the reason I have is because I teach statistics. So I know a lot of this useless trivia. But Marilyn Vos Savant is one of the smartest people in the world. Let me see if I can't find, let's see, I dug up a web page about her earlier. No. There we go. Marilyn Vos Savant. So women with the highest IQ, 5 consecutive years. She tested as high as 228. Wow, that's outstandingly high. Let's figure out her z-score. So her IQ was 228. So her z-score would equal 228 minus 100 divided by 15. So I'll help you out here. The numerator is 128. Then I'll help you out some more. 15 goes into 120 8 times with a remainder of 8. Now z-scores get rounded to the nearest 100th place. So that's going to be 18.53. Round to the nearest 100th. You'll see and appreciate the reason for that later on in this course. Right now, you'll just happily take my word for it, like that. So 8.5 standard deviations above the mean. That's pretty rare air. That's really rare air. So let's see if we can't get an appreciation for just how unusual that is. And in doing this, I'm also going to do a little bit of review for you. So let's think back to the empirical rule. Does anyone remember what the empirical rule says? Oh boy. Big fat silence there. All right, so let me look up which page the empirical rule is on. There we go. Empirical rule, page 104. So let's see if we can't go to page 104 in our book real quick. Don't tell me you sign me out again. But the empirical rule talks about a normal distribution and how much data you can expect within so many standard deviations of a normal distribution. So jump to 104. There we go. So basically, within one standard deviation of the mean, you should expect 68% of your data. Within 2 standard deviations, now you're up to 95% of your data should be within 2 standard deviations of the mean. Wow. Within 3 standard deviations, you got 99.7% of all of your data is within 3 standard deviations of the mean. So right there, it's just telling us that, you know what? After 3 standard deviations of the mean, you've only got 0.3% of your data. There's 3 people in 1,000 are outside of that range. So right there, that's pretty unusual. But remind me, how many standard deviations away from the mean was Marilyn? Like 8.5? Can you imagine how little data is going to be out there? She's got to be unique just about. There's just not that much out there. So not surprising that she's the smartest person in the world, or at least according to some. So nice little review of the empirical rule for you. But what's the one requirement to apply the empirical rule? What's one thing that you have to have going for yourself here?
Does it have to be a bell-shaped curve?
Perfect. Thank you, Amber. You have to have a bell-shaped or normal-shaped distribution. This rule states that for data sets having a distribution that is approximately bell-shaped, that means your normal distribution. Now, intelligence, fortunately enough for us, does have a normal distribution, but not everything does. And if something doesn't, then you can fall back on another theorem. So I remember his name, the Russian name, Chebyshev. Let's see. So Chebyshev doesn't know how to spell his name, neither do I. Chebyshev theorem. The nice thing about Chebyshev's theorem is that it works for any data set. So this is just review for you for next week. For any data set, 1 minus 1 over k squared times 100% of the data, or I should say at least that much of the data lies within k standard deviations of the mean. Well, for all intents and purposes, that's our k. Let's see how this would do in Chebyshev's theorem. Now, the nice thing about Chebyshev's theorem is that it works for any data set. It doesn't have to have a normal distribution. And you're going to get at least this percentage of data. Probably a lot more, because this is like a worst case. But for Maryland, it's going to be 1 minus 1 over 8.53 squared times 100%. Let me show that here on my calculator. So parentheses 1 minus 1 divided by 8.53, and hit the squared button on the left-hand side. Then a right parenthesis, and then 100. You don't need the times because your calculator understands that it's being multiplied like that. And it should give you about 98.6%. Yeah, there you go, 98.625%. So 98.625. Let's just round it off to 98.6%. So again, it's reflecting the fact that this is a really unusual observation. You don't get too many things that are way out there at the right end of a distribution like that. That's extremely rare. Okay. How are we doing on that one? Let's do one more from the section. Question on that one? This much here was a reminder or refreshing yourself for next week.
Okay. Yeah, I don't think we went over this.
Oh, we didn't go over Chebyshev's theorem last week?
No, we didn't, from what I recall.
Remember that?
I don't think so.
Okay, well, we got it now.
Okay.
So that's good.
So K is standard deviation number?
Yeah.
Okay.
Yep. So K, yeah, it's right here. So K standard deviations away from the mean. Tell you what, let's do another one then. If I didn't do it last week, so I'll make sure that we cover it this week. What percent of the data lies within, I'll let you pick it, 2 or 3. All right, K equals 2 standard deviations from the mean according to Chebyshev's rule. By the way, I've seen at least 3 different spellings of the name Chebyshev. I've seen it with a T. I've seen a K in it. Rumor has it that Chebyshev didn't know how to spell his own name. May or may not be true. But what is true is this little rule here. So it's going to be 1 minus 1 over 2 squared times 100%. So K is 2 in that case. Now let's stop and think for a second. What does the empirical rule say about 2 standard deviations away from the mean in the empirical rule? Well, the empirical rule would imply that you have normally distributed data. So maybe we do, maybe we don't, but if you did have normally distributed data, then according to the empirical rule, 95% of your data should lie within those 2 standard deviations of the mean. But if you didn't know that it was normally distributed, you couldn't use the empirical rule. But you still could use Chebyshev's rule. So that would say 1 minus 1/4, which is your 2 squared, times 100, or 3/4 times 100, which gives you 75% of the data has to lie within 2 standard deviations of the mean for any data set. Doesn't matter what it is, you have to have at least 2 standard deviations, or at least 3/4 of the data within 2 standard deviations. What that's telling you is if you're more than 2 standard deviations away from the mean, you're starting to become an unusual observation. Okay. Comments or questions on Chebyshev's rule here?
I have a question on the empirical rule
Yes.
theorem. So are you gonna, do we need to know like what all of them are, like values within 1, 2, 3, or? No.
So on the exams, you will have a lot of resources. Let's see, I can't think about it. You know, this is one that you kind of should know from heart. I'm not saying that this information won't be available to you, but the big thing you should know is the difference between the empirical rule and Chebyshev's rule. In as much as the empirical rule assumes that you have a normal distribution. The empirical rule only deals with values of 1, 2, and 3. In contrast, Chebyshev's rule deals with any value of K greater than 1. So, and the other thing about the Chebyshev's theorem is that it doesn't necessarily imply that you have normally distributed data. It works for any data set. So that's a nice advantage of Chebyshev's rule. So there's 2 kind of advantages. So you have to have these things memorized in terms of the empirical rule, 68, 95, and 99.7. Probably not, but you should know the meaty difference between these 2 rules. And that's the part I'm really trying to get across. So are you comfortable with that second part?
Yes, thank you.
Okay, appreciate it. Anything else on this one?
Really quick, how many questions are gonna be on the exam?
I haven't written it yet. Don't know. So let's cover one last little bit here with z-scores and measures of position and it's this particular problem. It asks us to use z-scores to compare the age of the winners for Best Actor and Best Actress for a given year. So we'll do that. And let me highlight for you some of the relevant information that we're going to need here for each of these two categories. So we're going to look at actors and actresses. And if we're going to calculate some z-scores, we're going to need to know the average age of the winners, the standard deviation of the winners, and the actual value for the particular year that we're working with. And then finally, we're going to calculate the z-score for each of these and compare the z-scores to try and find out which one is more extreme relative to their data set as opposed to the other one. So let's go back through and pick up some of these numbers. In a recent award ceremony, the age of the winner for Best Actor was 41, and the age of the best winner for Best Actress was 57. So that's our X's, 41 and 57 respectively. For all Best Actors, the mean age is 46.4, and standard deviation is 5.4. And those same numbers for women are 38.4 and 11.1. So something like that. By the way, which data set exhibits more variability? Actors or actresses?
Actresses?
Yeah, more than twice as much, right? Look at the standard deviation. It's huge. Even if you were to calculate the coefficient of variation, I'd still think it'd be even bigger, really. But let's just focus on the z-scores for each of these. So in terms of the z-score, you're going to calculate x minus x bar divided by sigma. So 41 minus 46.4 divided by 5.4. And over here, 57 minus 38.4 divided by 11.1. Now the first one, I don't think I need to take out a calculator to do that one, because that's just going to be negative 5.4 divided by a 5.4 gives me a negative 1 for z-score here. Now, I don't know if you caught it earlier, but in case your z-score doesn't work out nice and perfect, we're going to round our z-scores to the nearest hundredth. And in this particular case, I end up with about 1.68 for the z-score for Best Actress. So which one of these, Best Actor or Best Actress, had a z-score which was more extreme?
The actress?
Actress, yes, absolutely. It's closer to 2 standard deviations away from the mean, whereas this is 1 standard deviation away from the mean, okay? The fact that it's negative reflects that the winner this year was below the age of the average winner. That's okay. You're still 1 standard deviation away. Here, relative to this data set, you're about 1.7 standard deviations away. So in a relative sense, this is more of an extreme value. This is more unusual because you're farther away from the mean, and there's going to be less data out there. Any follow-up on that one?
Can we do another one that's like that one?
Let me see if I've got one. Sure. Let me see if I can't find it in the book. So this would be section 3.3. And that's going to be on page. The problem I want is going to be on page 125. So let me just jump to page 125. Problem number 14. Based on data set 1, body data and appendix B, males have red blood cells counts with a mean of 4.719 and a standard deviation of 0.490, while females have red blood cells counts with a mean of 4.349 and standard deviation of 0.402. Who has the higher count relative to the sample from which they came? Male with a count of 5.58 or female with a count of 5.23. So same kind of thing here. And let me copy down for us all the relevant data from this problem. And that would look like this. So this is example 14. So for males, we've got X bar is 4.719. Females, it was 4.349. Standard deviation was 0.490 and 0.402. The particular value we were working with was 5.58 for males and 5.23 for females. And so we want to calculate the z-score for each. So the z-score is going to be x minus this divided by sigma. So 5.58 minus 4.719 divided by 0.490. And we'll round that off to the nearest hundredth. Can someone verify this?
Negative 1.76. Yep.
I'm getting a positive 1.76.
I'm getting a negative for some reason. Maybe I'm sure I did it wrong. Oh, you know what I did? I did.
X bar.
Yep, I switched them.
Yeah, and that's important because if you got a negative, that would say you're below the mean, and that's not the case here. This person's above the mean. So yeah, just be careful with that. Now over here, same kind of thing, X bar, S, and X. This time you're going to get a standard deviation. It's going to be Z of 2.19. And I just don't have room for the calculation there. So which value relative to their data set is more extreme? Males or females?
Females.
Females, yeah. She had a red blood cell count, which was 2.19 standard deviations away from the mean, whereas the gentleman in the study had a standard deviation or a RBC count of 1.76 standard deviations above the mean. So this one is more extreme in terms of being farther away from the mean. Does that help?
Yes, thank you.
You're welcome. Thank you. Okay, that does it for section 3.3.